All right, so let's try some more examples from your book. So example 2.5, a motorist is traveling at a constant speed, 15 meters per second. It passes through a school crossing where the speed limit is 10 meters per second. A police officer is stopped there and starts the pursuit with a constant acceleration of 3 meters per second squared. So some keywords here. One are the first guy's got a constant speed. The motorcyclist is stopped, which means he's starting at rest and has a constant acceleration. So that means we can use our constant acceleration equations. And they want to know a bunch of stuff. How much time passes before the officer catches up with the motorist? What is the officer's speed at that point? What's the total distance each of them has traveled at that point? So what I've gone ahead and done is something that you guys should already be in the habit of doing, is that we're going to read the problem and then write down all the givens. So the officer had an initial velocity of 0. We're going to measure our position away from the officer, which is the school crossing, and then an acceleration of 3 meters per second squared. The motorist had an initial velocity of 15 meters per second. The system we're starting to model at when the motorist just passed the officer. So he's got 0 position as well. And no acceleration because he's traveling at a constant speed. This is our basic kinematics equation for position. And then we have a basic kinematics equation for velocity. And because this is constant acceleration, the acceleration is always the same. So we could just remind ourselves of that. Okay, so let's start off by modeling some of this motion. So it says, how much time will elapse before the officer catches up with the motorist? Catching up means when will he have the same position as the motorist. So what we're going to do is we're going to create 2 position equations, one for the officer and one for the motorist. So the officer's final position is equal to 0 meters initial position. Initial velocity was 0, so 0 meters per second times time, plus the acceleration of 3.0 meters per second squared over 2 times time squared. So all this cancels out, and the officer's position is given by 1.5 meters per second squared times time squared. The motorist expression is a lot easier. He does have an initial velocity but no acceleration. So the final position of the motorist is 0 meters per second, 15 meters per second times time, plus 0 meters per second squared over 2 times time squared. So this simplifies down to 15 meters per second times time. So we can solve this by equating these two. We want them to have the same position, so we set them equal to each other. 1.5 meters per second squared t squared equals 15 meters per second t. Now, in this class, whenever we cancel out a variable, in this case, we're going to divide both sides by t and get something new. Whenever we do this, we have to be aware of the solution we're losing. By reducing the power of the formula, we're losing a solution. In this case, the solution that used to satisfy the equation but no longer does is when t is equal to 0, and we have to be aware of if that's valid or not for us. It is a valid solution. It's when they first were at the same position as each other at the crosswalk or the school crossing. Now, it doesn't help us answer this question, so it's okay that we're eliminating it. And then if we continue farther, we can find that t is equal to 10 seconds. that's when they're going to have the same position as each other and the officer is caught up to the motorist. B says, what is the officer's speed at that point? So we can plug in for the officer's speed into this equation here. Got 10 seconds times the acceleration. So we'll do our, the officer started at 0 meters per second. The acceleration was 3.0 meters per second squared, and the time was 10 seconds. So the officer's final velocity was 30 meters per second. And the next question asked what is the total distance each vehicle has traveled at that point? So we can plug into either one of them. Probably the motorist is going to be the easier of the two to plug into. The motorist was traveling with a constant velocity, and they met after 10 seconds. So they're both going to have traveled 150 meters before the officer catches up to the motorist. Let's look at some of this with the graphing calculator. So remember the position equation for the officer and motorist were given by these two. So we're going to have the officer here and the motorist here, 15t and 1.5t squared. Let's go to zoom fit. We'll take a look at that. Now here I'm just graphing the first quadrant because anything left of time equals 0 isn't going to make any sense. And so there we go, and we can see the graph here of what's happening. The motorist is traveling at a constant velocity. Velocity is the slope in a position time graph, so we have a straight line. The officer started with a 0 velocity, so we have a 0 slope, and then was accelerating, so you can see the slope of this curve is slowly increasing. And then we could use the curve intersection function to show that those two lines intersect at 150 meters like we've got there, and that happens at 10 seconds. We could also graph velocity time functions, and so in this case the velocity function for the officer was 3.0 times time, and the velocity function for the motorist was just a constant 15. So then we can go to zoom fit again. So there's our increasing velocity of our police officer. And let's see the window here. Did I get them both turned on? No, I didn't turn this one on. Should have a magenta line here. There we go. So look at what's going on. Let's press trace here. After 5 seconds, the officer is not caught up to the motorist, but traveling the same speed. So what this represents is this is when the officer starts to close the gap. Starts catching up. Think about it this way. Here's the motorist is traveling at a constant velocity. The police officer starts at rest and slowly increases his velocity. So from 0 seconds to 5 seconds, the officer is traveling slower than the motorist. So the motorist is still getting away. However, at time t equals 5 seconds, the officer is now traveling the same speed as the motorist and eventually faster. So this is where we're closing the gap. We're starting to catch up. And look at what happens here. Remember that the area in a velocity time graph is displacement. This represents the distance that the motorist gets away from the police officer. And this represents, with the police officer's line on top, this represents the police officer regaining all that displacement, and the area of these two triangles is the same because right at t time equals 10 seconds, the officer has caught up completely to the motorist. Okay, Let's go on to a different problem. All right, a coin is dropped from the leaning tower. It starts from rest and falls freely. We want to just calculate its position and velocity after 1, 2, and 3 seconds. So really what we want to do here is just do this as quickly as possible, or not quickly, but as efficiently as possible. So we're going to write down our givens and the equations for position and velocity. Okay, so the y position and we know that it was dropped from rest. I say just dropped means dropped from rest. Yeah, starts from rest, falls freely, meaning it's under the acceleration of gravity. So we can plug information into this and say that the position after a certain amount of time is equal to, now they want to know here, they want us to measure the top as 0. So they want to know our position with respect to the top of the tower. So this is going to be 0, this is going to be 0, and this is going to be 9.8 meters per second squared, not negative 9.8, because downward has been measured as the, or no, sorry, they do want downward to be the negative direction. So we got to go with them if they list it out, otherwise it's our choice. So we're going to have negative 9.8 meters per second squared over 2 times t squared. That's going to be our position. And then our velocity function looks like that. We can plug in here as well. We'll start from rest. So there we go. What we're going to do, since we need to evaluate this multiple times, is we're going to put this into the calculator. There we go. That's our blue. There is going to be our position function. And then we'll have our velocity function here. There we go. So we'll quit back to the home screen and we'll put in vars, y vars function y1, and we're going to put in 1, 2, and 3. Okay, that's going to be our answers there. For A, and then we can do B. It's going to be y2 vars. And same thing, we're going to evaluate at 1, 2, and 3. So there we go. All right, we're going to run out of time here, so we'll have just one other short video to finish example 2.7. So click over to that now.